Okay, today's lesson is on Le Chatelier's principle. This is the last lesson for this section, and this is Henri Le Chatelier, and he's the chemist who came up with this idea of manipulating equilibrium systems. Okay, so the idea here is that we have systems that are at equilibrium, and what Le Chatelier found was that if you impose some sort of change, if you do something to knock the system out of equilibrium, what it will do is it will find a way to get back to that equilibrium. For some reason, the laws of nature tend to point towards equilibrium. And we'll talk more about why that is in the second semester when we get into thermodynamics. But for now, just accept that all chemical systems always achieve an equilibrium system. Okay, so what he found was that we disturb it. So the three things that we're going to look at that Le Chatelier found was that we can change the concentration, we can change the pressure / the volume, that's connected to Boyle's law, or we can change the temperature. Okay, so we were going to look at each one of these three changes to the system and see how it responds to that change. Okay, so here's the first one, concentration changes. So at equilibrium, what happens is those concentrations remain constant. Remember, we talked about that with the demonstration I did in class. The concentrations aren't equal to each other, they're just remaining constant. So if I change the concentration of any of the substances that are in that container, in that system, I'm going to disrupt that equilibrium. Okay, so here's what he found. If you change the system at equilibrium, you add something or take it away, the reaction is going to respond by doing the opposite. So if you add something to the reaction will consume it. If you take something away, the reaction will replenish it and start to put it back. So let's look at an example. Here's an equilibrium system, Haber's process for the production of ammonia. So we take nitrogen and hydrogen and we end up with ammonia. You got to picture this as a chamber. Remember, they're all together in a container, and we can start with nitrogen and we can start with hydrogen, but what we're going to do is we're going to start to produce ammonia. So these things are going to be constantly going back and forth. They're going to be making the ammonia and then breaking back down into the hydrogen and the nitrogen. So that's what we call equilibrium, where you got the forward reaction and reverse. Okay, so we let this get to equilibrium. That's these three lines here. Remember, they're staying constant. They're not changing. They're not equal to each other because this is your values for your concentrations, but they're not going to change if it's at equilibrium. Now, at this point in time right here, we're going to add more hydrogen gas. So we increase the hydrogen gas. So now, if you think about it, we just added more hydrogen in the container. So if I have more hydrogen in the container, isn't there now more hydrogen to collide with that extra nitrogen that's in there? Right? Isn't that going to react more often now with the nitrogen and produce more ammonia? Right? So we're going to have a decrease in the amount of hydrogen and a decrease in nitrogen and an overall increase in my ammonia. So if the hydrogen and the nitrogen are going down because they're being consumed and the ammonia is going up, we say that that reaction is now shifting to the right because it's reacting these two together more often, produce more of our ammonia gas. Okay, and eventually the reaction goes back to equilibrium. So that would now go back to our equilibrium system, and you can see the concentrations are now back to equilibrium. But the concentrations are now different than they were originally. Okay, the concentrations aren't the same as they were, but they've just reestablished this equilibrium where the concentrations are constant. Okay, so as a result of doing this, by putting more hydrogen gas in the container, we can actually produce more ammonia gas. And if you're trying to feed people by creating fertilizer, you want to have a lot of ammonia, so you want to put in a lot more of the nitrogen and hydrogen. Okay, and it makes sense. I mean, if you think about it, if I put more reactants in, I'm going to get more products out of it. So we can see that you're never going to get the reactants to go completely to zero, but we can put in so much of this that we can really keep shifting this further and further and further to the right. Now, what happens if I remove nitrogen? Well, if I take some of that nitrogen out, if I go in the container and I remove this nitrogen, well, now I don't have any nitrogen to react with the hydrogen. So what's going to happen now is that the ammonia is going to start to break down. It's going to start to produce more hydrogen. Oh, probably should say nitrogen first. And it's also going to produce more hydrogen. So we're going to get more hydrogen to go in the container. So we can see that if I take away the nitrogen, the reaction has to shift in the left, right? Because it's going to use up the ammonia. The ammonia's concentration is going to go down. I'm not going to have as much ammonia, and I'm going to start producing more nitrogen and hydrogen. Why is that happening? Because the rates of reaction are equal to each other. Remember we talked about rates, the speeds of the two reactions? Well, if I remove the nitrogen, I kind of disable this reaction, right? This reaction can't occur as fast as the reverse reaction. So therefore, by taking away the nitrogen, I have to, the reaction is going to respond by adding it back in. Okay? So that would be your concentration effects. So let's take a look at pressure and volume. This is one that throws students off most. Most students have the biggest trouble with this one. So we're just going to look at taking our container and starting it out at, like a size like this, so it has some volume, and we're going to change it to maybe a smaller volume. Okay, or we could change it to a bigger volume. So that's what we're going to be doing. We're going to be messing around with the volumes. Now, a lot of times they talk about pressure because if your volume goes down, you should know that your pressure goes up according to Boyle's law. Okay. Now, what I like to do with this is if we look at the ideal gas law, we say that the volume changes, right? We get a new volume. Well, the pressure is going to be, it's going to change, but it's going to have a new pressure that's established. Okay. So what is the reaction going to do if the volume goes down and the pressure goes up? Well, the only thing that the reaction can do, since we can't change its volume, its pressure is going to have to change. What we're going to do is we're going to change the moles. Now I like to look at volume and not pressure because pressure is a little confusing, but if we look at volume and the number of moles, it makes the most sense. Think about it. If I have a container that has a large, all these gas particles in here, right, and I make the volume get smaller, well, isn't there a smaller amount of space for those particles to occupy? So what the reaction will do is it's going to shift in such a way that it removes those particles from solution, or from the reaction. I guess it could be from solution. Okay, this is typically actually for gases. This doesn't work for aqueous systems, only for gaseous systems. So volume pressure changes only for gases. Okay, so the idea is that the volume of the container holding the gas reduces, the system reduces its own volume. How does it do that? By reducing its number of moles. Okay, so a smaller volume increases pressure, leaves the system with less space. Okay, so let's take a look at what we have here. So we've got this reaction here. Let's draw this out here. To the side. Okay, let's put in here the dinitrogen tetraoxide, and we have 2 moles of the ammonia. No, I'm sorry, the nitrogen dioxide. So what happens is the volume of the container is reduced. So if I make this go down, right, the reaction is going to go smaller. So my volume goes from a large volume to a small volume. Well, if we look at both sides of the reaction, now we got the two sides here. You got this and this, right? You've got this breaking down into nitrogen dioxide, and the dinitrogen oxide coming and forming the dinitrogen tetroxide. Okay, if the volume is getting smaller, this reaction is going to get cramped and squeezed. Okay, so you're going to have these particles in here, okay, are now going to have a smaller space to move around in, so they can't really move around in a lot of space. So what the reaction is going to do is it's going to try to make itself smaller. Well, on this side of the reaction, I have 1 mole, and over here I have 2 moles. Okay, so this would be of gases. So make sure you're following this. This is only true for gases. So we're looking at 1 mole of gas versus 2 moles of gas. So if my volume gets smaller, the reaction is always going to shift to the side with the smaller number of moles of gas. Because if I'm making this product, that's 2 moles, right? That's 2 gas particles that are going to float around in this container versus 1 big one. Obviously, this is a bigger molecule, but it's still not a bunch of separate molecules. It's all hooked together. So if the volume gets smaller, we're going to produce more of the dinitrogen tetraoxide. They're going to join together to make that. So what happens? Volume container reduced. Equilibrium will shift left to produce the smaller space, to go to the smaller number of moles. So I like to think of volume goes down, shift to the side, with lower number of moles. Make sure that this is of gas. Okay, so small. If I have a larger volume, shifts to the larger size. okay, the higher number of moles. Okay, we'll look at some more examples in class, but that's just the general idea of how it works.